So I'd like to start with a story, actually. So at the beginning of my PhD, I was interested in how robots could learn manipulation skills, skills like what's shown here, where the goal in this case was the robot wanted to figure out how to insert that red block into the shape sorting cube. And what it's trying to learn here is a neural network that maps from images, from pixels and taken from the robot's camera to joints, torques applied at the robot's joints. And as you can see here, what the robot is able to do is, through trial and error, it's able to start from scratch without having any knowledge about how to do the task to figure out a policy that can acquire the skill of putting the red block into the shape sorting cube. And here's an example of the final policy that it learned. So the bottom right is showing the images from the robot's camera, and the video, of course, is showing the skills that the robot's learned. And we were really excited about this result. So this was back in like early 2015. And the reason why we were really excited about this is that we had a general purpose reinforcement learning algorithm that could learn not just how to put this red block into the shape sorting cube, but could learn other skills as well. It could learn skills like placing the claw of a toy hammer underneath a nail for different angles of the hammer inside the robot's gripper. And the robot could use the same algorithm for learning, how to screw the cap of the bottle successfully. So this is pretty cool, and in follow-up work, we also found that the robot could use this, a variant of the algorithm to also use a spatula to lift up an object into a bowl. So we were pretty impressed with this, and we were pretty excited about this result. We had a general-purpose reinforcement learning algorithm that could acquire a wide range of skills. And a wide range of other labs built upon this work to learn other skills like hitting a puck into a goal, such as opening a door, such as throwing an object to hit a particular target. And at the same time, a number of labs were looking at these same sorts of algorithms for things like playing Atari games, like playing Go, and learning locomotion and simulation. So this is all really nice. It seems like we have algorithms that can acquire skills automatically for robots. But we have a problem. And the problem is that the robot didn't learn things like using spatulas to lift objects into bowls and things like opening a variety of doors. What the robot learned was something very specific. The robot learned how to use that spatula to lift that object into that bowl. If you change the spatula, or you change the object, or even if you change the tablecloth that's in front of the robot wouldn't be able to solve the task. And the same is true for all of the other things. If you change some small things about the environment, the policy that it learned would fail because it was trained in this one very narrow environment. And so in particular, what all of these things are doing is learning one specific task in one specific environment, starting from scratch. Now, okay, maybe you'll say, okay, this isn't a problem. We can solve this problem. We can just give the robot more spatulas, right? And then the robot will be able to generalize much more broadly and be able to generalize potentially even to a new spatula. But the challenge is if you look at kind of the learning process behind the scenes for many of these kinds of skills, you get something that looks like this. So the robot will be attempting the task through trial and error, and then a human comes in and needs to kind of put everything back for the robot so that they can try it again in that very specific scenario. And this is my friend Yevgen here, and one of the things you'll probably notice here is that Yevgen is doing more work than the robot is doing. This reinforcement learning process is supposed to be very automatic, but in practice, it's a very manual process. And it isn't practical to collect a lot of data this way, and as a result, it isn't practical to build robots that generalize in this way. With more data and with more diversity in the kinds of things the robot will see, the robot will generalize better. And so this is a problem because we're relying on detailed supervision and guidance. And this isn't just a problem, actually, with reinforcement learning and robotics. If you look at a lot of the machine learning systems that we have today, they have been able to generalize more broadly to different situations, but they're still learning one narrow task starting from scratch. And if you want them to do something different, you have to train them again and collect a large amount of data for that new setting. And this is a problem if we care about robots that can operate in a wide variety of environments and can perform a wide variety of skills for us. These are kind of all kind of very specialized systems that are acquired through machine learning. OK, and I think that if we hope to build machines and robots that can more generally understand and interact with the world, and such that we can put them in any environment and have them do useful things, then we may need to fundamentally rethink the way that we use machine learning in the context of robotics. Okay, so that's what I'd like to talk about in my talk today. So I would like to talk about how we might think about rethinking the algorithms that we're using when we're applying machine learning to robotics and the data that we're providing with our algorithms. And more specifically, it seems like the algorithms that we're using can't rely as heavily on the detailed supervision and guidance and have to learn something that's more general than a policy that's tailored for a particular task in a particular environment. And we need to be thinking about giving data to our robots, to our machine learning systems that isn't from just one environment, that maybe is inspired by some of the successes of things like ImageNet that can generalize much more broadly than the robot learning systems we have today. Okay, so first let's talk about rethinking the kinds of algorithms that we're using. It seems like we need something more general than a policy, because a policy doesn't allow us to perform a wide variety of things in a wide variety of situations. And in particular, if you think about the policy that was learned for the spatula task, what was learned here can't be used for anything else. So clearly, it seems like our robots aren't very intelligent. So what do we want instead? I think this is actually quite a challenging problem to think about. One thing you might think of, well, how about we just learn a task condition policy that's conditioned somehow on the task and in the environment that it's in, train it across a wide range of tasks and a wide range of environments. And I think this will be a lot better than the single task policies that we learned before, but it can only solve the tasks that were seen during training. It can't solve other tasks that weren't seen during training. So it seems like this is still missing something in terms of actually preparing robots for a wide breadth of skills that we might want it to perform in the future. So it seems like maybe what we want instead is something that we can use to perform lots of tasks, without having to know exactly what those tasks are a priori. And in particular, I think this is basically the ability to quickly adapt to new concepts, to new tasks, to new environments, such that when we see something that we're not prepared to see, such that our training wasn't specifically training us to do, we can adapt to that new situation. And this is where I think things like meta-learning come in. So we want to be able to acquire a prior over the kinds of policies and the kinds of environments that we might see, such that that captures essentially the functional aspects of everything that we've seen before, such that we can quickly perform a new task or a new environment by generalizing or adapting from our previous experience. And so this is kind of really the essence of meta-learning is. It allows us to learn the structure across multiple tasks or multiple environments, such that learning a new task or adapting to a new environment is very fast. Okay, so since many of you may not be familiar with meta-learning, I'll try to give a very brief overview of kind of what encapsulates meta-learning, although I actually teach an entire course on this topic in the fall quarters, so if you want to learn more, only a few minutes won't really do the topic justice. But essentially what meta-learning is trying to do is being able to try to adapt to a new task, and specifically trying to train for the ability to quickly adapt. And so we can see an example of this in the context of supervised learning, and say that we want to be able to learn a new supervised learning task with a very small amount of data. So as an example, say we want to learn an image classifier, and in particular, we want to learn an image classifier from 5 data points. So you might want to, here we're given 5 data points, where each data point corresponds to a different class. And we want to learn a classifier that can distinguish between each of these 5 classes, such that when it's given new images, new examples, it can classify those examples as being among one of the 5 classes on the left. Now, how might we go about trying to solve this few-shot learning problem, where you're only given 5 examples to learn from? Well, if you have data from other image classes, then you should be able to use that data in a way that can prepare you for this few-shot learning task. And in particular, what you can do is you can structure data from other image classes such that training and testing match. You can essentially structure data from other classes into these few-shot learning tasks, such that you train the model that you're learning, such that after it sees 5 images from one set of classes, it can generalize to new examples. And you can do this for you can construct a wide range of tasks, a wide range of few-shot learning tasks, such that when the robot or when the system sees a new task, as shown on the top, at test time, it can generalize and be able to classify new examples from just a very small amount of data, just 5 examples. So this is how meta-learning works in the context of supervised learning, where we have a set of supervised learning tasks from a very small amount of data, and we train our system to be able to generalize from a small amount of data. But you could also replace each of these supervised learning tasks with, say, reinforcement learning tasks or imitation learning tasks, where the goal is, given one demonstration, be able to perform that task in a new situation. Or given a small amount of experience in a new environment labeled by a reward function, you can learn a policy from that experience. Okay, so for example, if you want to look at it in the context of these sorts of problems in the context of reinforcement learning, say you want some simulated agent to be able to quickly adapt to new reward functions, you can train an algorithm such that after the meta-learning process, you get something like this, such that it's really ready to adapt, ready to run in any particular direction. And then you take a single gradient step with respect to the task of running forward, and you can get a policy like this. And likewise, you can take this policy and run a single gradient step with respect to the task of running backward, and you can get a policy that looks like this. So you can essentially very quickly adapt your behavior to different reward functions or different tasks. Okay, and you can also look at this in the context of imitation learning. So in some of our previous work as well, we've shown that given a demonstration for objects that the robot has never seen before, so this is a teleoperated demonstration, the robot is given this new demonstration with new objects, and it can learn a policy that can adapt to the objects in that scene, such that they can figure out how to place the apple into the bowl. Okay. And you can also take this, I guess, one step further and try to also meta-learn in such a way that you can learn very quickly from other sources of data, such as videos of humans. So you can, for example, take a video of a human, placing the peach into the red bowl, and it can figure out that it should adapt its behavior to the red bowl. Okay. So this is kind of the essence of meta-learning. It's the ability to train your policy such that it can very quickly adapt to new situations. Now, kind of the question is, let's get back to the setting of trying to learn something more general than a policy. Has meta-learning really accomplished this notion of being able to adapt very quickly or be able to acquire new skills very quickly based on our previous experience? Now, one of the challenges is that I would say that in some ways it has. We've been able to adapt very quickly to new situations based on previous experience, but we haven't seen the ability to adapt to entirely new tasks. So in each of these settings, the meta-training distribution of tasks correspond to really like one task with different variations on that task, like different objects or different directions. And it seems like we want to be able to instead try to actually meta-learn across a very broad distribution of tasks such that you could adapt to an entirely new task. And that might be able to get us closer to a robot that can perform a wide range of tasks. So can we adapt to entirely new tasks? If we want to do this, kind of the standard machine learning paradigm is that our training distribution and our test distribution must match. The same exact thing holds for meta-learning, but where your task distribution that you use for meta-training has to match the task distribution that you use for meta-testing. And so this means that if we want to adapt to entirely new tasks, then we need a very broad distribution of tasks for meta-training, such that we can generalize to an entirely new task. So where can we get a broad distribution of tasks? This is the kind of the first question. If we want to study these algorithms with very broad distributions of tasks. If you look at some of the simulated robotics environments that we have, you could look at things like OpenAI Gym. So these have lots of different kind of robotics tasks that you might consider. But unfortunately, there isn't a lot of shared structure between these tasks, and there aren't a very large number of tasks. So it may not be possible to try to learn a prior across all of these kinds of tasks in a way that generalizes to new tasks, because there might not be enough structure to latch onto in a way that allows you to generalize. And likewise, you could consider something like the Atari Learning Suite, where you want to learn a new game. But similar to Gym, these tasks don't share a lot of structure that might allow you to generalize and learn faster for new things. More recently, there was some work actually here at Stanford that was building a suite of tasks called the RoboSuite task or the Surreal task, the Surreal benchmark. And this is a step closer because these share a lot more common structure because they're different manipulation tasks, but there's only 6 tasks. And we can't hope to generalize to a new task given only 6 tasks. So motivated by this problem and by the challenge of trying to generalize to an entirely new task, we wanted to build a new benchmark that allowed us to study that. And in particular, the things that we want from this benchmark is that we want it to have a large number of skills. So we want it to have at least 50 distinct tasks. We want to have reward functions and success metrics for all of those tasks such that we can actually run reinforcement learning. We want all the tasks to be individually solvable such that we can focus on the problem of transfer and generalization rather than focusing on the reinforcement learning problem itself. And lastly, we want a unified state space and a unified action space such that there's some notion of shared structure among the tasks. And so motivated by this, we built a benchmark of 50 simulated manipulation tasks. So these are all shown here. And we're calling this the meta world benchmark in a sense that it's allowing us to study meta-learning algorithms more broadly than what we've been able to so far. And in particular, one of the things that we wanted to do with this data set is actually have a train set and a test set such that you can meaningfully study generalization to new tasks that the robot hasn't been trained on before. And hopefully this will allow us to study more general purpose robots and robots that can try to accomplish skills they weren't specifically trained to do. Okay, so now that we have this benchmark, it means that we can actually start to study generalization. And so that's what we did. So we ran meta-learning algorithms on this benchmark. And what we found is that a lot of meta-learning algorithms actually seem to struggle when trying to generalize across this benchmark. And in particular, if we look at a number of state-of-the-art meta-learning algorithms like MAML, RL squared, and Perl, if you look at the success rate on the meta-test tasks, you get a success rate around the 20s and low 30s. So this is perhaps a bit disappointing. Now, one question is, well, okay, why are they generalizing poorly? Why are they performing poorly on the meta-test set? And it turns out that they're actually doing very poorly on the meta-training set as well. And so this suggests that generalization actually isn't the challenge. The challenge is actually just fitting a very broad range of tasks with our function approximators, with our neural networks. And so then, okay, the natural thing to do is, well, what about just multitask learning algorithms? Algorithms that try to learn multiple tasks. This is kind of like a prerequisite to meta-learning. So we ran a wide range of multitask reinforcement learning algorithms, and these methods also seem to struggle when we tried to train them across all of the 50 tasks in the benchmark. Okay, so why the poor results? What are these algorithms struggling with? So we had a range of hypotheses. One is that maybe it's an exploration challenge. So reinforcement learning, exploration is a challenge in reinforcement learning, and so maybe they're just having trouble finding the skills and figuring out how to get reward. But all of the tasks are individually solvable on their own. So it means that reinforcement learning algorithms can find the solution to these things when you try to learn from scratch. So that doesn't seem to be the challenge. Maybe it's a data scarcity problem, but we gave all the methods really plenty of data in order to be able to learn from. We also gave all the algorithms plenty of model capacity. So it doesn't seem like it's a problem with data scarcity or model capacity. And it turns out that if you train policies independently on each of the tasks, that actually does better than if you train policies jointly on the tasks. So actually trying to fit all of the tasks in the data set is actually harder than trying to fit them individually. And so from this comparison, our conclusion was that the challenge is an optimization challenge. Essentially, it's having trouble. It has plenty of capacity to fit all of these tasks, but it is having trouble optimizing for a policy that can perform all of the tasks successfully. Okay, so to try to actually solve this optimization problem, we looked at a number of prior literature on multitask learning, and some of the biggest number of approaches that we saw were trying to perform architectural solutions. So they would try to change the architecture of the neural network in a way that could facilitate transfer better. And it's possible that some of these approaches could help the problem that we're seeing. But at least from our take on this literature, it didn't seem like there was any really principled approach for thinking about these architectures to try to mitigate the particular challenges that we were seeing. And we didn't really have a good sense for which of these architectures would necessarily solve the problem that we're seeing. Now, a couple of other algorithms, instead of trying to change the architecture, tried to change the optimization process, and that was more appealing to us. So in particular, what these algorithms try to do is try to weight the tasks in different ways, such that if you have, for example, 3 different tasks, you try to learn a weighting or kind of change the way that these tasks are weighted such that the optimization problem is easier, such that they can focus on the tasks that are making the most progress or the tasks that are the most difficult for the current algorithm. But when we ran these algorithms, it turns out these algorithms also didn't work well for our setting. So it seemed like it wasn't just how the tasks are weighted. And in particular, to try to control for this, we tried to very evenly sample all the tasks and make sure the objectives were all on the same scale. So how do we kind of solve this multitask optimization problem? Well, we had a couple hypotheses for what might be going on. And our first hypothesis is that the gradients from different tasks are often conflicting with one another. And in particular, the way that we mathematically define that is that we see this negative inner product between the gradients of different tasks. Essentially, if there's more than a 90-degree angle between the 2 gradients. And this seemed like a reasonable hypothesis, because if they were pointing in the same direction, then you would see positive transfer between the tasks. But this can't be the only problem, because if this is the only problem, then it seems like you should just be able to average the gradients and get the direction that effectively optimizes the sum of the objectives. And so the second hypothesis that we had is that when they do conflict, they cause more damage than was expected to be caused. And what I mean by that is that you have high curvature in your optimization landscape. And in particular, we can look at a very kind of toy visualization of what I'm talking about here. So say you have some optimization landscape. The parameters you're trying to optimize are theta, and the loss function is L. You have a landscape that has high curvature that looks something like this. If you are at this point in the optimization landscape, and your gradient looks like this, say this is the optimization landscape for one of the 2 tasks that you might be trying to optimize, and maybe the other task is trying to push the parameter vector to the right. And then if that other task is trying to push the parameter vector to the right, then according to the gradient, you'll suffer some increase in the loss function for this task. That would be reflected by something like this. But in reality, if you actually take that step, you end up somewhere like this. So the loss function, basically the error that you incur from the conflict in the gradients, because the gradient from the other task was pushing you to the right, causes more damage in the loss function than was reflected in the magnitude of the gradient. OK. So our hypothesis is that we have this issue with curvature, right? And the way that we tried to address both of these hypotheses is that when the 2 gradients are conflicting, it seems like what we can do is try to not cause damage to the gradients. Essentially try to solve a constrained optimization such that you are minimizing the loss functions of the task, subject to the constraint that you're not making any of the tasks worse. And that might address this challenge here, where you will try not to make this task worse, because you might actually make it worse than you were expecting to make it. And concretely, the algorithm that we came up with for doing this is a very, very, very simple algorithm. Just take your existing optimization. If 2 gradients are conflicting with one another, then project the gradient onto the normal plane of the other gradient such that it's orthogonal and doesn't affect that gradient. And likewise, do the same thing for the other gradient. So if you have 2 gradients, the red one and the green one, project the blue one onto the normal plane of the red one, and project the red one onto the normal plane of the blue one. And then these gradients seem like they won't interfere. You might make slower progress, but it seems like you'll mitigate the challenges associated with underestimating how much damage you might do by going in the wrong direction. And if the gradients don't conflict, then just leave them alone. So this is a really, really simple change that you could implement in really only a few lines of code. And if you run this on the, we call this predicting conflicting gradients, or PCGRAD, a fairly intuitive name. And if you run this on the Meta World benchmark, we find that in comparison to training independent models, you're able to significantly better optimize these tasks together. And in comparison to trying to train them jointly, it is able to learn and optimize much quicker and also achieve much greater performance. So it seems like, from these results, it seems like the optimization really was a big issue here. And by projecting the gradients onto the task, we're able to learn many, many more tasks than we were able to learn together before. So in the case when we're trying to train across all 50 tasks, we can solve around 30 to 35 of the tasks in a single neural network policy. And as a side note, it's also worth mentioning that we tried this type of approach on supervised learning problems as well, such as a multitask CFAR example, as well as a computer vision setting where you're trying to predict segmentation depth and surface normals. And what we found is that by combining this approach with architectural solutions to multitask learning, such as routing networks and such as MTAN, you're able to boost the performance of those approaches by a significant margin, and really across the board in all of the settings. OK. So now you might ask, okay, why does this multitask optimization work? And we wanted to kind of test if our hypothesis about the conflicting gradients and changing the direction of the gradient was what was solving the problem. And one of the things that's worth noting is that when you project the gradient onto the normal plane, you're actually changing both the magnitude of that gradient as well as the direction of that gradient. And so we ran an ablation where we compared this approach with only changing the magnitude or only changing the direction of the gradient and keeping the original magnitude or direction the same. And we found first that both, those two ablations are shown in blue and red. We find that both changing the magnitude and the direction is important, but changing the direction is really where most of the gain in performance is coming from. So this suggests that really, this sort of suggests to us at least some evidence that this hypothesis about positive curvature is actually what is going on in these neural networks. OK. Cool. And this work was quite recent, within actually the past few months. And so our next step here is to actually try to go back to the meta-learning setting and actually study a setting not just where we're training across a set of tasks, but also testing generalization to entirely new tasks by learning a prior with meta-learning. OK. So takeaways here. First, scaling to broad task distributions is hard, harder than you might think. But if you train across very broad task distributions, such as MetaWorld, and hopefully we'll see more benchmarks come out in the future, and mitigate optimization issues, then you can actually get positive transfer from training across multiple tasks, and actually sometimes train better than training models independently on each of the individual tasks. OK. So now that I've talked about algorithms, let's talk about data. So at the beginning of this talk, I showed some examples of robots learning tasks, such as using a spatula or inserting a block into a shape sorting cube. And if you think about the data that we're training, the data that the algorithm sees in this case, it has a single object or a couple objects. It is in a single environment, and it's of a single task. And so of course we won't be able to generalize if this is the data that we're feeding to our algorithm, right? More recently, there's been some progress in this direction. So we've seen algorithms such as these different works that can generalize to new objects. This includes some of the meta-learning work that I showed at the beginning. But they're still in a single environment and are really inherently trying to think about a single task or a single task family, such as placing objects into containers or such as grasping objects. More recently, I think we've seen even more progress on this front. So we've seen a number of works, including some work here at Stanford as well, that is able to generalize to many objects and is also looking at many different tasks, which I think is important for thinking about generalization. Yet these works are also still in a single environment. And so if you think about these works from kind of the context of machine learning, where we're kind of used to training on very large and diverse data sets, the data still that we're training our robots on doesn't compare to anything like ImageNet. And we can't expect anything like the generalization of ImageNet if we're training our algorithms on this. We still have like a single viewpoint, a single environment. It's really kind of a very narrow data set. Now, this is the machine learning perspective, that we're not really training our robots on very large data sets. But from the robotics point of view, maybe it's not practical to collect ImageNet for every experiment that we want to do, right? So we don't want to have to collect all that data on our robot. And if we have this paradigm of setting up an experiment, collecting ImageNet, and then running our reinforcement learning algorithm or our robot learning algorithm on that data set, that's not going to be practical in the future. We can't replace this collect data step with a collect ImageNet step. So instead, I think we need to be thinking about how we can try to accumulate and reuse data across environments and across institutions. Now, the challenge here is that every institution has their own robot, has their own experimental setup, has their own camera. And so what this means is that we need to start investigating whether or not we can share data across robot platforms, across lab environments, across experimental setups. And if we can do that, then I think we can actually start to get to the scale of something like ImageNet. Okay, so can we accumulate data across labs? This is kind of one of the questions that we wanted to study. And the first step to studying this question is actually just collecting a data set. And so that's what we did. We collected a data set that is somewhat summarized by the visual here that has 7 different robot platforms in it, including Sawyer, Franka, Baxter, Fetch, KUKA, WidowX, and a robot at Google. It has 113 camera viewpoints across the different experimental setups. It has 15 million video frames, so in quantity it's also quite large. And it was also collected across 4 different institutions. And for each of these robots, it isn't just a new robot platform, but it's also at a different institution with a different experimental setup. And also importantly, it's open for contributions. I think that this still doesn't really compare to something like ImageNet, but it's getting closer to that setting. Okay. So then we need to actually test if this data set is useful, if we can actually use this data set in a meaningful way to aid in generalization. And this question is non-trivial because we're kind of very attuned to the setup where we're learning in one experimental setup with one robot. And so what we do is we need an algorithm that can learn from offline data sets. And a lot of reinforcement learning algorithms are kind of learn instead from this online experience that's collected from the policy rather than an offline data set. And so we took an approach from some of our prior work that can learn from offline data sets that basically what it does is collects data, it learns a model from that data. So in this case, it's learning a model of what the next images will look like given the current image and the sequence of actions. So you get videos that look like this. It's basically a neural network. It's basically a dynamics model, but in visual space. And then once you learn how to predict, you can plan using that model using your favorite planner as long as it can scale to video prediction models. Okay, so this is the approach that we'll use to try to learn from the data. And to evaluate whether or not it's useful, we will we'll take the data set that we collected, which we're calling somewhat shamelessly RoboNet, inspired by ImageNet. We're going to hold out one of the robots. We want to be able to test if this data set can be used to generalize to an entirely new robot. So we hold out one of the robots, and then we fine-tune on a new robot platform. And we're not just fine-tuning to a new robot, we're actually fine-tuning to a new robot, a new environment, a new set of objects, a new camera viewpoint, essentially an entirely new experimental setup. And when we fine-tune the video prediction model on this data, we then evaluate the model on basically the planning algorithm on a set of tasks. And what we see is that if we, for example, hold out the KUKA, fine-tune on this set of data, we get a success rate around 40%. Whereas if we train from scratch on only 400 trajectories from the KUKA, we get a success rate that's significantly lower, that's around 10%. And even if we actually train from scratch on the KUKA with significantly more data, with 1,800 trajectories, we still perform worse than if we pre-train with the RoboNet dataset and fine-tune on the KUKA. Now you might say, okay, well, maybe this is just the KUKA. We also ran experiments on the Franka, where we held out the Franka and then fine-tuned on the Franka. And we're again seeing this performance improvement from pre-training on this much more diverse data set of robot interactions. And we also ran experiments on a Baxter as well. We also saw a gain from 33% to 58% by pre-training on RoboNet. But the last thing that we observed in this setting is we ran an ablation where we also pre-trained on only Sawyer data and then fine-tuned on the Baxter data. And this method actually performed the best. So this suggested to us that there's actually a lot of work to be done with these very large data sets because we're essentially seeing underfitting. When we add data on top of the Sawyer data, our performance degrades. And so that means that we're not capturing the diversity of the data and capturing all of the information that's in that data because our model isn't able to fit that data. So in general, we view this hopefully as a step, in contrast to kind of the things that I showed at the beginning, hopefully the step towards more generalizable, learning more generalizable skills in more open world environments. But of course, a lot of important directions for future work to try to mitigate some of the challenges associated with fitting these very broad data sets. Okay, and then one last thing is, what about other data? So I showed how we can use data from other robots, but there's lots of other data that's out there, lots of other video data. For example, on the internet, there's lots of videos of humans doing things. And it seems like we should be able to leverage that data in ways that also inform how to act in the world. So as an example, if you go on YouTube or on the internet, you can find videos that look like this, for example. Or maybe in a more modern era, you might find more modern videos. And these videos, I think, are actually provide a huge opportunity for us because, first, they're a very broad, untapped source of data that contain many, many interactions in many, many environments. And second, they include more sophisticated interactions than the kinds of interactions that we can collect at scale with robots. They contain interactions of people using tools and people flipping objects using a frying pan, for example. So it seems like if we can use this data, then we might be able to learn more complex skills and also be able to generalize more broadly. But there's a number of challenges, of course. So first, there's a huge domain shift between the kinds of videos that we'll see here and the kinds of videos that our robot is observing. And second, we can't access the actions that were taken by the human. So we can't directly figure out how the human was doing the things that they were doing. And even if we could access the actions wouldn't correspond to the same action space of the robot. Okay, so because of some of these challenges, we wanted to take a first step in this direction. And the way that we wanted to do that is to learn from videos of humans in the robot's environment. And so in particular, we wanted to see if the robot could learn how to use a variety of tools by essentially watching humans use tools. So what we did is we took some examples, basically took videos of humans using tools. This data is really easy to collect in comparison to teleoperation data of the robot using tools. And we also used interaction data, such as the kind of data that we had in RoboNet of robots interacting randomly in the environment. And from this data, we learned a predictive model of videos, and then planned using that model to accomplish tasks. Now, the key challenge here is how do you learn a predictive model in settings where you don't have the actions and where you have domain shift? And the way that we approach this problem is we formulated a graphical model underlying kind of the data that we have. And in particular, we decided to model, well, first, we can only observe the action half of the time. So we have this semi-observed action variable where it's only observed in the setting where you have interactions and not observed in the setting where you have observations. And then we have a latent action variable z that's modeling essentially the intentions of the agent, whether it be a human or a robot. And then lastly, we have a domain variable d that's capturing basically the differences between the robot domain and the human domain. And this is observed because we assume that we know whether or not we're looking at a video of a human or a video of the robot. And then we essentially augmented our video prediction model with these latent variables, and then optimizing using variational inference by optimizing the evidence lower bound. Okay, so how does this work? The first question is, can our model leverage the observation data to improve? And to do this, we compared first to SAVP, which is a standard video prediction model, but that doesn't have the ability to learn from videos of humans. So it's only trained on the random robot interaction data. And we also compared to an oracle that was this standard model, but was trained both with random robot interactions as well as demonstrations, kinesthetic demonstrations of robots using tools where we can observe the actions. And what we see is these are two standard video prediction metrics that measure the quality of the predictive model that was learned. And we see that we're able to outperform a model that's trained only on the random interaction data, and also start to approach the model that is trained with kinesthetic demonstrations. We think this result is significant because even trying to make use of the robot data and trying to get anything out of the human data is I think, is really a hard problem. But of course, these metrics aren't very useful. And really the question that we actually care about is, can this observation data improve performance? Can the robot actually learn how to use tools and basically perform tasks that require tools better by leveraging the observations of the humans? And so what we did is we evaluated the robot on a sequence of tasks. In particular, we gave it tasks such as trying to move objects, trying to move a set of objects to the right, where it's going to be a lot faster to use a tool, to use basically this pencil case as a tool to push the objects over to the right. And the robot can figure out by planning with its learned predictive model how to grasp the object and move and use it to push the erasers close to the pencil. And we also give it other tasks. So in this case, the goal is to push a pear onto a plate. And the robot can figure out how to grasp a spatula and push it onto a plate. And likewise, there's a task. We had a task of pushing some trash near a dustpan, and the robot can figure out how to grasp the sweeper and use it to push things near the dustpan. And quantitatively, we want to study if the observation data is actually improving task performance and compared to just using the interaction data. And we find that we see a significant gain in the success rate by using the observation data. So essentially, the robot was able to use both seen and novel tools by watching humans use tools. OK, so to conclude this part of the talk, I think that if we want robots to be able to generalize, we need to be able to accumulate and use all of the available data that we have at hand, whether it be data of robots at other labs or data from humans. And hopefully this will be kind of a step towards making machine learning methods for robotics much more generalizable. And I guess it's also worth mentioning that this idea really isn't new. This is kind of the approach that everyone in the machine learning community has been taking to build more generalizable models of language, models of images, et cetera. And so I think that this is really a step towards trying to take robotics outside of really kind of the dark ages of machine learning, where you're only training your machine learning models on these really tiny data sets. OK, so in summary, I talked about how we can try to rethink algorithms and rethink our data, such that we can try to scale the very broad task distributions by mitigating some of the optimization challenges, and to accumulate large and offline data sets with off-policy model-based reinforcement learning algorithms. And I think that hopefully by doing so, we can maybe kind of bring ourselves one step closer to having robots that can more generally perform tasks in a wide variety of environments. Now, what's next? I'd like to talk a little bit about some open challenges and maybe where we're at with regard to those open challenges. And to do this, I'd really like to think about just a very concrete example of something that's maybe remarkably challenging for the current things that we have today, but also remarkably easy for humans. So say, for example, you have some environment, maybe a kitchen environment, and you put your robot in that environment. And maybe this is a kitchen that the robot has never seen before. Kind of the open challenge is just, let's see if the robot can make us a bowl of cereal in that new environment. This task, I mean, for those of you that are familiar with some of the challenges of robotics, this is, in many ways, I think, like really a grand challenge. This is something that's remarkably challenging. But of course, for humans, this is really a simple challenge. And I think that if we can think about steps that can bring us closer to going in a new environment and doing really a simple skill in that environment, but maybe a skill that requires reasoning about partial observability, reasoning about long, kind of dependencies in this sort of longer horizon task, then we might be closer to having systems that are more intelligent and have more common sense. And to get to kind of a system that can do something like this, I think that we need basically to get to intelligent behavior in open world environments, I think we need systems that can continuously learn and improve from data that they collect in the real world, such that they can start with more simple skills, like some of the skills that we saw earlier, but move towards more and more generalizable environments and more complex skills. And in this sort of process, I think that there are a number of challenges. I think that we can try to address some of those individual challenges now. So things like adapting to a new environment that you haven't seen before. And one way that I think we can view this is actually in the context of meta-learning. So we can view the online adaptation problem as a few-shot learning problem, and we have a little bit of work on trying to see how robots can adapt with very small amounts of data to new environments. Another challenge and another kind of important step towards moving towards this goal, I think, is to move towards longer horizon tasks. So a lot of the things I talked about today were relatively short horizon skills. And it seems like we need to figure out how we can bootstrap from those short horizon skills towards longer horizon skills. And one way that I think we can do that is through things like hierarchical abstractions. We have some early work on this direction where we try to optimize for sub-goals such that we can string together a sequence of short skills to perform a longer task. And lastly, I think one considerable risk here is that if we want to continuously have our agents continuously learn and improve to perform like more and more difficult tasks and perform in more and more general environments, then one challenge that might come up is what if the improvement is too slow? What if we won't ever actually get to the kitchen environment at the end because the process of getting better is just simply too slow? And I think that this is where things like meta-learning can actually come in as well. And I think that if we can, over the process of learning a sequence of skills, at the beginning learn very slowly because we're learning from scratch, but over time get faster and faster at learning based on the experience that we've seen so far, then we might be able to accelerate this process of improvement and hopefully get towards the more challenging environments more quickly. Okay. Lastly, if you're interested in learning more about some of the algorithmic challenges and algorithmic advances in this direction, as I mentioned earlier, I'm teaching a course on multitask learning and meta-learning in the fall quarters, and actually all of the lectures will also be available on YouTube through SCPD in the future. And also, in the context of reinforcement learning, I helped form a course at Berkeley on deep reinforcement learning, which has been continuing to taught, and all the lecture videos there are also available online. And really, these two courses capture a lot of the kinds of algorithms and methods that I was talking about today. And of course, there's also reinforcement learning courses at Berkeley, such as some of the courses that Emma Brunskill teaches, for example. Okay, and with that, I'd like to thank my students and my collaborators, and I'd be happy to take a few questions. Thank you. Yeah.
Yeah, so I have two questions. By the way, thanks for the great talk. It's really nice ideas. One is about like the generalization performance. How do we really know the limits? So when we train a robot, it's not going to work in all possible environments. So before deploying the robot, how can we really understand the limitations? And the second question is, like, so all these tasks are very different to, say, ImageNet, where the robot really has to interact with the environment. So do you think it's better to take very good quality data rather than gathering a lot of data? And is there a way to do that?
Yeah. So I'll start with the first question. And I think this is a really challenging question. Basically, once you learn some behavior or some policy or some model, how do you know the extent of the generalization of that setting? And in general, I think that in many ways, sometimes, like in some ways, this falls under the problem of uncertainty quantification. Like, given a model and given a new data point, can my model tell me whether or not it can generalize to that data point or not? And there's been a lot of work in that direction that I think is making some progress, although in the context of deep learning and neural networks, it's a very, very challenging problem. The other thing worth mentioning is that I think that if we hope to generalize to that thing, then we should just try to broaden our training distribution such that we can hope to cover that task or that setting that you're going to see, that data point that you're going to see at test time. And I think that in many kind of cases, when you think about generalization, you think about, okay, given my data set, can I get my robot to generalize? But I think that the better way to do is, like, how can I broaden my data set and get my algorithm to work on that data set? And think about how ways that you can actually go about collecting very large data sets. And that's essentially the kind of work that I was showing towards the end, where we want to generalize and use data that's very broadly applicable and covers the kinds of situations that we might want to see at test time. Regarding the second question, you were asking about when we collect data for robots, we want to collect interaction. And we may want that interaction to contain more sophisticated interactions with the world, basically focusing on quality over quantity. And I think that this question is really important, and I think that I showed a data set of, that we're calling RoboNet of completely random interactions with objects. And if you wanted to, for example, learn how to use a spatula to lift up an object, like that data isn't going to help you very much. You aren't going to get very far to performing that very complex task. And so I think that we need to be thinking about both quality and quantity when we collect these data sets. And one of the things that we want to do next in this data set is start to augment it with more sophisticated interactions. So there's some other work at Stanford called Robotics, for example, that is looking at how we can really scale teleoperation. And that might be one way to get more sophisticated interactions of robots interacting in a wide variety of settings. But you could also imagine using reinforcement learning as well. So if you actually start learning from this data and start learning skills, and you can actually deploy policies that are learned to collect more data in a wide range of environments, such that you can start to get more interesting interactions and interactions of the robot actually trying to do tasks in a very goal-directed way, while still trying to maintain the quantity. Because I think the quantity, and really the breadth, not necessarily just the quantity, but the breadth of the data is going to be really critical for generalization. Yeah?
Maybe a follow-up on that, about the breadth of the data set. Just thinking about the difference between ImageNet and the tasks associated with it, which tend to be classification, segmentation, counting instances, whatever. There's a high-dimensional input space, perhaps, in terms of the number of pixels and their values, and the output space is fairly small.
Yep.
But for an interaction task, both are so much bigger. You have a whole environment that you can have all kinds of images coming in the video input, whatever your observations are, and your decisions are extended over time.
Yep.
And you're choosing a whole trajectory. So could we maybe say that speaking about broad data sets is like intractable, like you just can't have breadth in the sense that ImageNet has breadth? Does that make sense, what I'm trying to kind of
Yeah,
say?
so ImageNet is interesting because it has both breadth in some cases, because it has just so many environments and so many objects. But in other ways, it actually doesn't have that much breadth because it's only the kinds of images that a human would take, like with the camera. And it doesn't contain like all of the other kinds of observations that a robot sees that a human sees, because I think it was taken from like Flickr or something like that. They're basically like things that humans would take pictures of. And that actually doesn't capture a wide range of images that robots might see in the environment, especially mobile robots and basically like all these sorts of viewpoints that you might not see. And so in some ways, the kind of the breadth that we might need for robots actually might be much broader than what we need for something like ImageNet. So that's my first thought.
So I guess my point was, it seems like we cannot collect that kind of breadth in any, like to get to the point where you can say this is a broad data set, because there's so much more to collect. Like you said, we even need more than we have in ImageNet.
Yeah, I guess in some ways it seems like we should actually be better off in robotics than ImageNet, because we can have robots collect the data for us. Whereas for things like ImageNet and computer vision, like we're having humans collect the data. And we actually have, if we can get enough kind of low-cost robots, for example, out there collecting data, then we may actually be able to collect data that spans a really wide range of situations and maybe a much wider range of situations than the kinds of things that we see with ImageNet. So I think that there is some hope there for trying to capture that really broad distribution. But at the same time, I do think that really there's going to be situations that the robot sees at test time that aren't captured in that, simply because of how huge the space is. And there are situations where humans are in that all the time, and we also need algorithms that can reason about situations that they haven't been in before and kind of understand things more broadly. And I think that that's really a tremendous challenge as well, beyond just capturing broader data.
So, I hate to occupy the question stage, but just final follow-up on that. You mentioned at the end hierarchical abstraction, which I think is the key for humans being able to deal with so many tasks even unseen, because we have this understanding of physics, of bodies in some sense, and we're able to plan in a very low-dimensional space in comparison to just a giant neural network black box model of the environment. So do you think that might be like the key, or just kind of combined with readable data?
Yeah, so I think that part of the key is, so I think that like collecting as broad of data as we can, it makes a lot of sense. But part of the key also is you don't want to model everything, because if you try to have your neural network model all of that data, then you're just going to hit a wall at some point, because it's not possible to model everything in the real world, and you have to figure out what to discard. And figuring out what to discard is really, I think, also a critical challenge. And somehow that what you discard actually needs to also be informed by functionality, by semantics, And some of that is going to have to come from humans. So instead of trying to model everything, you could try to model only the tasks that humans care about, similar to some of the meta learning things I was talking about, like only model a prior over those task-relevant skills or human-relevant skills. But then the challenge there comes in is like, how do you define the things that are relevant? Is it a human? Is it some part of the algorithm that's kind of trying to figure out what to discard and what to keep? And I think that sort of it's sort of like a compression view on artificial intelligence. Like, what do you keep, and like in a lossy compression scheme, what do you keep and what do you throw out? And that I think is an open challenge. Yeah.
So when you project the gradient of one task, when you're training multiple tasks at the same time, when you project the gradient of one task into the normal plane of the other task, so when there are more than 2 tasks, how do you do that?
Yeah, so when there are more than 2 tasks, what we do is we for each task in the batch, we do the same procedure because we want it to be symmetric, and then for each task in the batch, we randomly sample an order of all the other tasks, and then do it iteratively, where you first look if it conflicts with the first one. If it does, you project. Then you take the result of that and go on to the second task. Okay, thank you.